Hey there, welcome to a video lecture for Physics 121. Today we're going to talk about momentum. So we're going to talk about momentum, impulse, conservation of momentum, center of mass, and the motion of the center of mass. And what I want you to think about in this is I want you to think about how this approach is complementary to Newton's second law and Newton's third law. And at the same time, it's also a useful complement to what we've been dealing with energy. So for this, I want to start out with a straightforward example. And what I'm going to do is use this example to derive and define new quantities. And then we're going to see why they're useful. So let's consider two interacting bodies. Okay, these are just two masses with mass 1 and mass 2. And they have a pair of forces acting on them, which is a Newton's third law pair. Okay, so there are no external forces acting on this system. That's important. And the internal forces are defined by Newton's third law. And what we're going to see is that there's a quantity called momentum that, as long as Newton's third law holds, is conserved in the same way that energy is conserved if there's no external work done on the system. Momentum is conserved if there are no external forces on the system. So in this case, we know the net force on each body, and we can derive this change in velocity for each body. And this will be different if the masses are different. Let's work through that a little bit. Okay, so we have this mass here, which I'm going to call F2 on 1, and this is F1 on 2. So this is mass 1, and this is mass 2. Okay, so we have F net of mass 1 is just equal to F2 on 1, right? F net equals mass times acceleration. Therefore, F2 on 1 is equal to m1 a1. Okay? If this is some constant force, then we can multiply both sides by time. And since we know that A delta t is equal to delta v, right? Then we can say, okay, delta v is equal to F2 on 1 over m1 delta t. Okay? Now, we can do the same thing for F2, for m2, right? We can say, okay, F1 on 2 is equal to m2 a2, right? These are vector quantities. And then using again a delta t is equal to delta v. Now this is v2, this is v1, right? Then we get delta v2 is equal to F1 on 2 over m1 delta t. Now, you might ask, why am I doing all this? And the answer is because these are third law pairs, right? Therefore, F2 on 1 is equal to minus F1 on 2. Okay? Therefore, F2 on 1 delta t plus F1 on 2 delta t is equal to 0, right? Because the delta t is the same, and these are the same. Or I should say these are equal and opposite, right? So what does that mean for these two equations here, right? So if I multiply both sides of the left equation, I can get m1 delta v1 is equal to F2 on 1 delta t. On this side, delta V2 M2 is equal to F1 on 2 delta T. Right? So these values plug into this equation. Therefore, M1 delta V1 plus M2 delta V2 equals 0. Okay? Whenever you have something in physics where the sum of various things is equal to 0, you should sit up and take notice, because this is what is often, this isn't necessarily a conservation law, but it is useful and it usually means something deeper. Okay? So to go back to this PowerPoint for a little bit, this slide is basically just what I showed you already on my iPad. So I'm showing it to you here a little bit more formally. Feel free to pause the video and think about it, right? And then we're going to define something out of this quantity that's going to be very valuable. And that is that this M1 delta V, okay? So we're going to define this M delta V by little p, okay? Don't ask me why momentum is p. M was taken by mass already, okay? So we need another variable. The unit of momentum is kilograms meters per second, which should be obvious because it's a mass times a velocity. There isn't a derived unit for momentum, so we don't have anything like joules that you have to keep track of. So for the particular case of two interacting bodies, we have this equation here. M1 delta V1 is equal to minus M2 delta V2. Okay? And the change in the two bodies is, in the momentum of the two bodies is equal and opposite. Total momentum is conserved during the interaction. Any momentum lost by one is gained by the other. So I want you to see a complementarity here and an echo of conservation of mechanical energy, right? So what we saw in with the conservation of energy is that if there were no dissipative forces and there was no external work being done on the system, we could conserve a quantity called energy. And now what we're seeing is that if there's no external forces on the system during a collision, we can also conserve a quantity called momentum. This quantity is a vector quantity, which means it allows us to determine the direction of particles. So now we need to define another quantity called impulse, which is the change in momentum, okay? And this is the integral of force over time, right? You can prove this, but I just want to show you this derivation, and let's sit and look at it for a second. Okay, so you should note that like most integral derivations that we've had before, you can have an average force, which is the change in momentum over time. This is analogous to an average velocity or an average or a change in position, right? And you can also have, by just taking the derivative, the instantaneous force. Both expressions usually refer to the external forces acting on a system, where the system is defined as whatever this momentum you define it as. So this would be the momentum of a system. And you'll notice I use this word system again. Okay, it's used in the same way that I was using it when we talked about energy, right? Where if energy is gained or lost in a system, in the same way you can have momentum gained or lost in a system. So let's see three different time-dependent forces, and we want to compute the impulse on an object of mass m due to each force, right? So you should recognize that the impulse is the integral of the force over time, and this is related to the area under the curve, right? So feel free to pause the video, work this out yourself. I have the answers underneath, but you should be able to just quickly work through this yourself. So pause for a second, and when you come back, I'll go over how to think about this. Okay, you're back. Let's go over this real quick. Just made this small so I can sketch a little bit. So for the first one, right, we have 2F0 and 6T0, so the force is on. Therefore, the area is just the area under a rectangle that is 6, let's say, seconds by 2 newtons. Okay, and so the impulse of 1 is 6F0, 2F0 times 6T0 is equal to 12F0T0. Okay, the second one is 4F0 times 3T0, so this is 3 by 4. And this, 3 times 4, F0 T0 equals 12 F0 T0. Okay? The third one, right, is 2 by 12, but it's a triangle. Therefore, this is half the area of the corresponding rectangle. So what's the point here? Many forces as a function of time give the same impulse or the same change in momentum. So if you arrive at the same change in momentum, there are many different ways to get there. And again, I want you to see an analogy here between this idea and conservation of energy. If you remember, with conservative forces, you have many different ways to get the same change in kinetic energy of your system with different forces. So let's take a worked example real quick. A ball of mass m strikes a wall at normal incidence with speed v. The ball rebounds along its incoming path with speed v. What is the ball's change in momentum? So for this example, we have a ball with some mass m and v. So this is v initial. And this is v final. Okay, so the ball comes in, it bounces off the wall, it comes out. Right? What is the change in momentum? Velocity and momentum are vectors. Therefore, the change in momentum depends on the direction of the ball. So, if we say that this is the x direction, for example, and this is y, then delta p is m v final minus v initial. V initial is, let's say it's heading in the positive x direction, so this would be v x hat, right? This is the speed. V final is equal to minus v x hat. Therefore, delta p is the mass, v final minus v x hat minus v x hat, right? So this is v final, this is v initial. Therefore, delta p is 2mv. Okay? So this is useful, right? This is the initial momentum, the final momentum, minus the initial momentum, x hat. Note, this is a vector, okay? So we still have the change in momentum is still a vector quantity. The magnitude of p is 2mv. Now I want you to consider two masses that move toward each other, and then they collide. Okay? In this case, m1 is greater than m2. what happens? So we can do this a couple different ways. We can work through this as a net force problem, a free body diagram problem, or we can work through this as a momentum conservation problem. I'm going to show you how to do this as a free body diagram problem first, and then we're going to go and work through this as a momentum conservation problem. So first I want to draw a free body diagram for M1 and M2. Okay, so this is M1, right? This is, let's say, X, this is Y. Gravity points this way, so it has some weight, it has some normal force, and when M1 and M2 collide, there will be a contact force of M1 and M2. So this will be F21, and there will be some F12. Okay, so these are the free body diagrams for mass 1 and mass 2. They both have some weight, they both have some normal force, and F21 and F12 are equal and opposite. What that means is that there's no external force, right? Therefore, the sum of delta P is 0. In other words, delta P1 is equal to minus delta P2. Okay? So next what we need to do is we need to calculate the initial and final momentum of this in this particular case. So for this case, right, the initial momentum, P I1 is equal to M1 V1I, and P2I is equal to M2 V2I. Okay? Therefore, M1 V1F plus M2 V2F, so this is the final momentum, is equal to M1 V1I plus M2 V2I. Now I'm just making sure that everything that needs to have a vector should have a vector. And this is the initial momentum. You'll notice in this equation, I haven't actually solved the problem. Why? I have one equation and two unknowns. Right? I don't know V final, V1 final, and I don't know V2 final. I know M1, I know M2, I know the two initial velocities, so all of these quantities are known, and these two are unknown. So I need one additional piece of information to solve this problem. It turns out that one additional piece of information is conservation of energy. I need to know where the energy is going in my system, and then I can solve this problem. So we're going to get to that very soon. Before I go further, I want to talk about something called the center of mass. So far we've defined momentum, and we've defined impulse. I'm going to define some third quantity called the center of mass. And this is a point representing the average position of the matter in a body. It does not need to be located within the body. In fact, in many cases, it's located between two bodies. A body can be treated as if all of the external forces act on the center of mass. We're going to start with some simple examples, and then we're going to move to some more complex ones. For a two-body system, this is found from the center of mass, which you'll notice is in units of distance, because it has units of x here. is m1x1 plus m2x2 over m1 plus m2. This is effectively a weighted average of the positions of the particles that compose a body. So a larger mass is more important. In 3 dimensions, we write the center of mass as the weighted sum of the vectors of the positions, where the total mass is the index mass. Okay? And so the center of mass has x, y, and z components. And so for 2 bodies, you can think of this as essentially the weighted components. Let me give you an example for 2 bodies in 2 dimensions so that you can see what I'm talking about here. So, for example, particle A is at the origin and particle B is somewhere. Where must particle B be located so that the center of mass, marked with an X, is at the point 2, 5? So, to start working on this problem, we should know, right, that what we need to do is we need to have 2 centimeters equal MA XA plus MB XB over MA plus MB. Okay? And we need to have 5 centimeters equal MA YA plus MB YB over MA plus MB. Okay? There are a few things that are helpful here. One is MA plus MB, if we remember, is 30 grams plus 10 grams, which is 40 grams. And the other thing is that XA YA equals 0, 0. Therefore, we can reduce the equations above, these 2 equations, to 2 centimeters equals MB XB over 40 grams, and 5 centimeters equals MB YB over 40 grams. MB is equal to 10 grams, which we can then put here and here, right? So essentially 2 centimeters equals 10 over 40. Note this number is unitless, x, b, and 5 centimeters is equal to 10 over 40, yb. Okay, so our b is equal to 8x plus 20y centimeters. So that is our answer. Now, what does this tell us? Well, you'll notice the center of mass is closer to the origin than it is to B. Why? Because B has a relatively low mass compared to A, right? So that means this number here, 1/4, is smaller than 1, meaning that B is weighted more lightly. Okay? Now, what if you want to do this with more than 2 particles? So, we'll give you another example. The position of 3 particles are 4, 0, 2, 4, and -1, -2. The masses are 4, 6, and 3 kilograms. Where is the center of mass? So, I'm going to do the x component first, and then we'll take a look at the y component. So, the x component of the center of mass is m1 x1 plus m2 x2 plus m3 x3 over m1 plus m2 plus This is just writing fully out this equation that I have from before. Okay, so this is 4 kilograms times 4 meters. That's m1, x1, plus 6 kilograms, 2 meters, plus 3 kilograms, minus 1 meter. All over 4 plus 6 plus 3 kilograms. Okay, this, it turns out, is equal to 1.92 meters. By the way, feel free to pause the video at any time. You know, the order of what I'm saying matters a little bit, but the rate at which I'm saying it is not. So if I'm going too fast, feel free to pause. If I'm going too slow, feel free to skip ahead. We can do the same thing for the y component, right? And you end up getting 1.38 meters. I encourage you to do this on your own. Okay, so the next thing I want to talk about is I want to talk about what the system's center of mass has to do with conservation of momentum. So imagine that we have a system of particles with a center of mass vector defined okay? Or let's say the total mass times the center of mass is equal to the sum, okay? So all I've done, this is the total mass, okay? What I'm going to do is I'm going to take the time derivative of each side, assuming that none of the particles change their mass. So now what we have is d dt sum of mass I r the center of mass is equal to the time derivative of m I r I. Okay? So if the masses are constant, right, then this side, the derivative goes inside the sum because this is constant. Therefore, the sum of the masses, dr of the center of mass, dt, is equal to, and this is important, the sum of mi dri dt. What's this? This is the velocity of particle I. Okay? Therefore, we can define this as what we call the center of mass velocity, okay, which is the time derivative of the velocity of the center of mass vector. And this is now the total mass times the center of the velocity of the center of mass is equal to the sum of mi vi. What is this? This is the momentum of particle I, right? So therefore, this, okay, is essentially the momentum of the whole system, which is equal to the sum of the momenta of the individual components. Okay? Or we can define a center of mass velocity, which is equal to the sum of the momentum of all the components over the total mass of the system. We can also do something else that's fun. let's take another derivative. Okay? So now we have m, the total mass, and we're just going to take a derivative of the center of mass velocity. This is equal to the time derivative of the momentum. I'm going to write the right side of this equation a little bit differently. Okay? Now I'm going to bring the derivative inside. What's this? This is acceleration, right? So that means that this is equal to the sum of mi ai. What's this? This is the net force on particle I, right? Therefore, this is the sum, I apologize for my crappy sum notation, there we go. Therefore, the derivative of the center of mass velocity, in other words, the acceleration of the center of mass, is the sum of the external forces acting on the system, right? Because if there were any pair of particles acting on the system, they would be subject to third law pair forces. So only external forces can change the sum of the net forces on the system. Okay? What this means is, going back to our original formulation, what is the center of mass good for? The center of mass only accelerates when there are external forces. Okay? Center of mass only accelerates when there are external forces on the system. So I'd like to stop here and summarize. The momentum is a vector quantity. It's given by the mass times the velocity. The impulse is the integral of the force over time, and you can show that this is equal to the change in the momentum of a particle. Okay? So if you integrate the force over distance, you find the work done on a particle. If you integrate the force over time, you find the change in momentum of the particle. Momentum is conserved during an interaction if the sum of external forces are zero. In analogy, I want you to think about this as analogy to the internal energy of the system is conserved if no external work is being done on it. Okay? Then we define this property called the center of mass, which is the weighted sum of all the masses in the system. And we showed that the motion of the center of mass, the velocity and the acceleration, are related to the net forces acting on the system, right? So let's think about what the velocity of the center of mass might mean and why this might be helpful. So if you remember from way back in the kinematics unit, we talked about different reference frames. So we talked about how if an object is moving at constant speed, you can transform into that reference frame, and then all of the other objects will be moving at different speeds in your system. But critically, the forces don't change because the forces only deal with acceleration. And so now we're going to see one particular reference frame that's very useful, which is the center of mass frame, when this center of mass velocity. So there's a reference frame where the center of mass velocity is zero. And this is very valuable because it means the total momentum of the system is zero. And if there are no external forces acting on that system, then the total momentum of the system will always be zero. And this is very powerful in the same way that you saw how energy conservation is very powerful. And so for the next couple of classes, we're going to be looking at some examples of how to work with this and how to solve problems that we weren't able to solve before. A lot of these problems are going to be collision-based problems. So we're going to have two objects, they collide, they go apart. Critically, conservation of momentum allows us to deal with this problem without ever knowing what the forces on those objects were. And because in the case of arbitrarily hard bodies, for example, if you have two pool balls colliding, those forces become very, very large very quickly. And we don't need to calculate that because all we need is the impulse, or the total change in momentum. And I'm going to show you how to do that soon. Alright, thank you for watching. I hope you found this helpful. Please let me know if you have any questions, and I'll be happy to discuss anything from the topic of this lecture. If you want me to go over it in the next class period, I'm happy to do that. If you want me to go into more detail, I'll be happy to do that. Otherwise, I have a lot of worked examples to work on. I think this will all make a lot more sense once you see some examples, which I'll be posting videos of shortly. Thank you.